All right, hello. We're going to look at some simple related rates problems, and they're word problems, of course. Um, and I think the best way to start is just to look at an example, and then I'll go over the steps, and then I'll do more and more examples. So here we go. Okay, let's take a look at this. A spherical balloon is inflated with helium at the rate of 100 pi feet cubed per minute. How fast is the balloon's radius? Balloon. I know is balloon. How fast is the rune? Is the rune? What? How fast is the balloon's radius increasing at the instant the radius is 5 feet? All right. So these aren't related rates. And rates are derivative, like instantaneous rates of change that involves the derivative. So the first thing that we're going to do here is just draw a picture of balloon. Well, so we have a picture of a spherical balloon, and I'm going to label anything that changes, I'm going to label it with a variable. That's the first thing that we're going to do. So if the balloon, I'm just trying to think about the situation, if the balloon is being inflated with helium, then it's expanding, so that means the radius is changing. I'm going to label that R. The volume is changing. I can't really label that well. And then the surface area is changing. So I have all of those. So first I'll draw a picture, and then anything that's changing, I'm going to label with a variable. Now all of these things are changing with respect to time. And then the next thing I'm going to do is write down the rates that are given to me. And there's one rate, I think, that's given, and that's the rate at which the balloon is being inflated. So if you think about this, a spherical balloon is inflated with helium at a rate of 100 pi cubic feet per minute. The 100 pi cubic feet per minute, that's volume, you can tell because of the feet cubed, but it's also a rate, so it's the rate at which volume is changing. And the way that we represent that, so like we're going to write down the rates, but we're going to write them down with math notation. So the rate at which volume is changing, that's going to be dV dt, because this is all changing with respect to time. So the rate at which volume is changing with respect to time is given by 100 cubic feet per minute. And then I write down with math notation what rate they want me to find. So how fast is the balloon's radius increasing? Well, that means dr dt, dr dt, and I usually do like a little question mark. Okay, so the first step is to draw a picture. Second step is to label anything that's changing, label it with a variable. Then write down with math notation, with calculus notation, the rates that are given and the rates that are required. And then the next step is to, so we wrote down the rate that's required, and we want to know when it's required. So when it says at the instant the radius is 5 feet, so when r equals 5 feet. Now it's very, very, very important not to plug in anything until we've already taken the derivative, and you'll see what I mean by this. So don't plug this in yet. It's like there's nothing to plug in. Like what to plug into? What are you talking about? Okay, you're crazy. Watch. So the next step. So first we drew a picture, then we wrote down variables for anything that's changing, and then wrote down the rates that we have and the rates that we want and the instant that we want them. And then the next thing to do is to write down an equation that relates these variables. Now in this case, it's talking about how fast the balloon's radius is increasing. The instant the radius is 5 feet. Okay, so we're trying to relate the radius and the volume of the balloon. So based on what the question is asking for, I know that I have to relate the radius and the volume. So it didn't talk about surface area at all. So I'm going to leave that out for now. So the equation that I'm going to write down is just the equation for volume. What is that given by? Well, that's just V equals 4/3 pi r cubed. So now I have related radius and volume. So there we go, 4/3 pi r cubed. Alright, recap steps again. That's crazy, so many steps. First, you draw a picture. Then you draw or write down variables for anything that's changing in that picture. And then you write down the rates that are given with calculus notation. Write down the rates that you want and the instant you want them. So that was this part and that part. And then write down an equation to relate the variables. Now we had to look at the problem to see how to relate these, but it's pretty simple. And then the next thing to do is to take the derivative of this. Now we're going to take the derivative with respect to time because everything is changing with respect to time. The volume is changing with respect to time and the radius is changing with respect to time. That means, given a certain time, you get a different volume, or given a certain time, you get a different radius. So that's what we're going to do. We're going to take the derivative with respect to time and see what we get. Well, the derivative of v with respect to t, that's the derivative of v like normal. We're going to use implicit differentiation here. That's the derivative like normal, because remember, those don't agree. So the derivative of v would be 1, and then tack on a dv dt. So it's implicit differentiation. All of this, 4/3 pi, that's just a coefficient. So I'm going to take the derivative of r cubed. That would be 3r squared. Tack on a dr dt. I'll simplify a little bit. And I get that. So now I took the derivative with respect to time, and now I have an equation that relates the rates. Look at that. I've related the volume rate with the rate at which the radius is changing. It's like I'm doing related rates. It's amazing. Okay. Then the next thing you do is plug stuff in. If you ever get stuck, you always go back to the original equation, but in this case we don't get stuck because we have, look at these, we have dv dt, that's 100 pi, okay, and we have r, which is 5. Now it was important not to plug in r right away, because if we did, then it would seem like this is a constant. We would take a derivative of that and we would get 0. But it's not a constant, so we have to leave it as a variable. So this would be 5, and we're trying to solve for dr dt. So I'm going to plug everything in. This video is getting too long. And that equals 4 pi times 25 dr dt. How do I know I was going to solve for dr dt? Well, that's this. That's what that part is telling me. Okay, and what is that? Divide both sides by 100 pi. And what do we get? dr dt equals 1. And then we have to come up with units. Well, this was feet cubed. Like, we could just think about it, but feet cubed on this side, and then we divided it by feet squared. So then we just get feet. Well, this is actually feet cubed per minute. So it's 1 foot per minute. Minute? Were we doing this in minutes? Yeah. And there we go. That's how you do that. If they asked a question about surface area, then we would find a way to relate volume and surface area. It's pretty simple. Okay, I'm going to be done with this video. We're going to do another example and another problem. Actually, we're going to write down the steps first and then do another example.